A worm's eye view of the world. Suppose yourself a worm, the Bible says you are anyway, and crawling around on a sheet of paper. With your vermicular mind, you doubtless would take a superficial view of the universe and find it as impossible to imagine a third dimension as man does a fourth. If in the course of your crawling you came across a triangle, you might, if you were a measuring worm, pace it off and find that the distance from corner A to B was 8 inches, from corner B to C was 6 inches, and from this data, if you knew the law of the hypotenuse, you might calculate that the distance from corner A to corner C was 10 inches. On measuring it, you would find your prediction verified, and so gain perfect confidence in your plane geometry. But unbeknownst to you, poor worm with your eyes fixed on the paper, some man may have picked up the sheet and crumpled it up or rolled it over so that corners A and C are only 1 inch apart in the third dimension. The worm is right when he thinks that the distance between these points is 10 inches. So is the man right when he says it is 1 inch. It depends on the point of view. Now in Einstein's view, something of this sort happens to our three-dimensional space when matter gets into it. We know, for instance, that if you divide the circumference of any circle by the diameter, the ratio figures out as 3.1415, etc. It has been calculated to 707 decimal places, but we can dispense with the rest of them and call the whole thing pi for short. Write it with the Greek symbol for pi, and it looks more learned. Now, if you place a heavy particle, say a lead bullet, in the centre of a circle, the ratio of the diameter to the circumference, according to Einstein, becomes a little less than pi, for the circle has been warped, so to speak, into the fourth dimension by the strain of gravitation. The difference in such a case is too small to be measurable by any known means, but it is supposed to be an actual, not an imaginary, deviation from the geometrical law. Now, the sun being a big, heavy body, must extend its gravitational strain for a considerable distance around, and a ray of light passing through this crumpled up space would not be able to pursue a straight course, and, according to the eclipse observations, it does not. Light, like everything else, follows the easiest way, and this is not always the straight and narrow path. A river takes the easiest, not the shortest, way to the sea, and this leads it through many meanderings. Most of us, I suppose, have a mental image of Newton's gravitation as a sort of rope by which the sun pulls the earth into its orbit when it is disposed to fly off on a tangent. But from Einstein's viewpoint, we should rather think of the earth as picking its way as best it can through a space and time combination that has been strained and distorted by the power of the sun. I visualize Einstein's solar system as a spider web, with the sun in the middle like the spider, and the planets, like flies, trying to get around through the tangled strands. But it is more complicated than that, for each planet has its own lesser web of radiating influence to drag about with it wherever it goes. Newton's idea is simpler, but unfortunately light at least seems to follow Einstein's law, not Newton's. That is why Einstein is such a troublesome fellow. If he would confine himself to metaphysical speculation, nobody need bother about these strange notions of his. But when he points out how they can be proved, and then British astronomers and American physicists find things according to his deductions, he cannot be ignored. The man does not seem to have that decent respect for the opinions of mankind that leads most of us to limit our logic to the sphere of common sense. When he gets an idea in his head, he follows it wherever it leads him, even though he bumps up against Euclid and Newton and the rest of us. For instance, if you admit the second of his two fundamental postulates, that the speed of light is constant, regardless of the velocity of its source, you are irresistibly led, unless you let go of his hand somewhere on the way, to the conclusion that time is a local affair, that there is no way of telling by light signals whether two clocks at a distance are keeping the same time, or whether two events at different places occur simultaneously. You could not tell this even if you could shoot a watch from one place to another with the speed of light, for no matter how many seconds or years the watch might be on its way, it would register the same time. If instead of a watch a man could travel at that speed, he would not grow old on the way. According to Einstein, no man, watch, or any other material thing can travel with the speed of light, for it would require an infinite force to get the smallest particle such a velocity. But let us suppose that a hollow projectile holding a man, such as Jules Verne and Wells used on their voyages to the moon, should be sent off into space with a velocity 1/20,000th less than light. If at the end of a year the projectile should be caught like a comet by the gravitation of some star and be swung around and sent back to the earth, the man on stepping out of his shell would be 2 years older, but he would find the world 200 years older. This would be, as Professor Langevin suggests in Scientia 1911, an interesting way to study history, but it would be risky, not to say impossible. Still, French scientists like Napoleon have no place in their dictionaries for so stupid a word as impossible, and Monsieur Esnault-Pelterie has figured out that 1,000 pounds of radium would be sufficient to carry a man to Venus in 35 hours if a hollow projectile could be fitted up like a rocket with the radium in the rear sending out a rapid fire of electrons. Turning time backward. To loosen up our conventional ideas of the fixity of time and space, we may accept the aid of the scientific romancers. Camille Flammarion, the famous French astronomer, wrote a fantastic little book called Lumen, which tells of a man who died in 1864. His soul flew straight to its heaven, which was one of the planets of Capella, the largest star in the constellation Auriga. Here he found the benevolent inhabitants of that sphere, who were endowed with superhuman powers of sight, watching with great distress the bloody scenes of the French Revolution of 1793, and wondering how it would come out. To the visitor from the earth this was an old story. To the people of Alpha Aurigae it was a present spectacle, for the distance of the star was such that it took like 72 years to travel from the earth, so they were 72 years belated in their observation of current events on our planet. The spirit of the defunct Parisian, having the power of flying through empty space at any speed he chose, found that he had thereby also acquired control of time, and could hasten, retard, stop, or reverse the course of events at will by simply varying his speed. If he remained stationary, scenes on the earth would unfold at their normal rate and in regular order. If he travelled away from the earth with the speed of light, everything seemed to stand still. If he travelled faster than light, he overtook the rays that had left the earth farther and farther back in the past, so he saw through them events in the reverse order. For instance, when he looked down on Waterloo, he saw the battlefield strewn with corpses, and Napoleon walking towards Waterloo backward, pushing his horse by the bridle. This is how the battle looked to the interspatial observer. When my sight was sufficiently habituated to the scene, I perceived some soldiers coming to life out of the eternal night, and by a single effort standing up. The dead horses revived like the dead cavaliers, and the latter remounted them. As soon as 2,000 or 3,000 men had returned to life, I saw them form unconsciously in line of battle. The two armies took their places fronting one another, and began to fight desperately with a fury that one might have taken for despair. As the combat deepened on both sides, the soldiers came to life more rapidly. At each gap made by the cannon in the serried ranks, a group of resuscitated dead filled up the gaps immediately. When the belligerents had spent the whole day in tearing one another to pieces with grape-shot, with cannons and bullets, with bayonets, sabres, and swords, when the great battle was over, there was not a single person killed, no one was even wounded. Even uniforms that before it were torn and in disorder were in good condition, the men were safe and sound, and the ranks in correct form. The two armies slowly withdrew from one another, as if the heat of the battle and all its fury had no other object than the restoration to life, amid the smoke of the combat, of the 200,000 corpses which had lain on the field a few hours before. What an exemplary and desirable battle it was! Another literary curiosity on the same theme is Ignis, by Comte Didier de Chousy. This tells of certain engineers who attempted to utilise the internal heat of the earth by running the waters of a lake into a deep boring. The result was an explosion that blew off a piece of the planet. But the passengers on this artificial asteroid, on looking down through their well at the earth they had left, could see the lake and city undisturbed, and watched themselves at work as they were before the place blew up. The explanation was this fragment of the earth was projected into space more rapidly than the speed of light, and so was catching up with the rays that had gone out before the explosion. These rays, of course, carried the picture of earlier scenes. But Einstein would say that this story, as we might ourselves have suspected, must be fiction, for according to his theory the speed of light is the absolute limit of motion, the infinity of velocity, which no material body may excel or attain. He does not, however, say anything about the possible speed of a disembodied spirit, such as Flammarion employed in his imaginary exploration of space. The metaphysics of the movies. But from such fantasies we can see that the order in which we view events depends upon how fast and in what direction we are moving, and that past and future may be reversed to our vision. This is easily made apparent by means of motion pictures. If the film is reeled off in the wrong direction, the action is reversed. So we see divers rising gracefully out of the water and landing on the springboard. Newly hatched chickens, dismayed at the sight of this unfriendly world, calmly tuck themselves back into their broken shells, which close in upon them. When we have come to the close of a perfect Thanksgiving Day, the obliging operator may give us an encore of the dinner reversed by running his machine backward. Then we see pieces of turkey politely picked out of the mouths of the diners with their forks and replaced upon the plates. When these are passed back to the carver, he puts the slices neatly in their places, and the fowl is then sent back to the oven to be unroasted. The cook then sticks on the feathers. The hired man carries the turkey out to the chopping block, where, with one swift stroke, he restores the head, and the fowl runs off backwards. This is just as correct as the ordinary order. The sequence of events is the same. Cause and effect are linked together as firmly as before, only they have exchanged places. A scientist knowing nothing of our world except from watching such reversed motion pictures might deduce from them the same consistent and logical system of natural laws that we now have, although some of them, for instance the second law of thermodynamics, would be reversed in form. The motion picture man has also the power to alter the speed of the passage of time as he will by turning the crank faster or slower. Sometimes he is quite too careless in the way he employs this prerogative. If he is behind time on his schedule, he will rush through a lazy siesta scene in a Mexican plaza with all the fury of a Max Sennett farce. But this telescoping of time can be used to advantage, as when he shows us the growth of a plant, the unfolding of its flower, and the ripening of its fruit, all in 15 minutes. On the other hand, motion may be slowed up by taking twice as many pictures a minute as usual and projecting them at the ordinary rate. For instance, if it is a dog jumping up to grab a piece of meat from his master's hand, we see the dog rise slowly from the ground and, while poised in mid-air, eye the meat carefully to select the best point of attack, then deliberately take it between his jaws and gradually descend. Now, notice that this is just as true a picture of the dog's jump as any other. The movie man has simply expanded time measurements as he expands space measurements when he shows us a close-up. A close-up with a face covering a 16-foot screen is just as true as a smaller picture. It is what we should always see if the lens of our eyes were a bit more convex. We look through the small end of an opera glass and objects seem magnified. We look through the large end and objects seem minified. This is not an illusion. The opera glass does actually enlarge or reduce what we see. So, too, time intervals can be lengthened or shortened. Take a dose of hashish. No, don't, I should say. If you did take a dose, you would find that your perception of duration was prolonged. If while under the influence of the drug you drop a book, it will seem an hour getting to the ground. De Quincey describes such experiences in his Confessions of an Opium Eater. But without entering into such abnormal states, we all know by everyday experience how time flies or lags according to the number of our sensations. Bergson's philosophy is built upon the distinction between the idea of duration, as experienced by all of us, and the idea of time, as established by the physicists for comparative measurements. Festus says, "We live in deeds, not years, in thoughts, not breaths, in feelings, not in figures on a dial." For all we know, an ephemeral insect that dies in a day may live a longer life than a Galapagos turtle that exists for 2 centuries. What Mark Twain said about classical music applies also to science. It is not so bad as it sounds. The thing that the chemist calls sodium chloride, other folks call salt, and so does he when he is off duty. Don't let the scientist bluff you by his polysyllabic propensity. Just try to see what he means by such language. Now, what these new-fashioned non-Euclidean geometricians call the four-dimensional space-time continuum is essentially the same system of reference as you have used ever since you could toddle. Minkowski did not invent it. Everybody thinks that way, unless he is an idiot. Each one of us has had to build up his own philosophy of the universe long before we went to school, mostly before we could talk. We had to study geometry while we were in our cradles. Worse than that, we had to work out a practical system of geometry for ourselves, without the help of Euclid or anyone else. We had to excogitate a system of relationship between the sights and sounds and touches that came to us before we could get along in the world. Probably we all solve this riddle of the universe in about the same way, although since there is no way of directly comparing notes, we cannot be sure about that. End of section 5.